Hi, this is Grover, Blue Collar Codes, Quick and Dirty, episode 23, going over linked lists. You can find this file, episode 23.py, in the GitHub repository linked in the video summary. So what we're covering is, what are linked lists and the implementation thereof, kind of joining these 2 points as one, and then why use a linked list versus an array, and then just briefly touching upon how you can utilize linked lists as a stack or a queue. And we'll dive into deeper implementations of this in the next episode. So what is a linked list? Essentially, you're using class instances called nodes traditionally to store a value and then a reference to the next node, usually called self.next. Now, a singly linked list is just how I described it right here, in that there's only one reference and it's pointing forward or pointing in a direction to the next element in your list. And as you're going, you're creating new nodes and you're creating new elements, and you have a link to the first node you create, and then all of the nodes link to the next node until you reach the last node, which has a self.next of none, and then you've reached the end of your singly linked list. Now, doubly linked lists simply have another reference point here, another attribute in this class node, and it'd be self.previous. Now, to dive into a bit of how you can create your own linked list to get a better idea of how you need to traverse it, what you can do is you can just follow along and create your own nodes and then update your own references to those nodes. And here, just make note that I called node 1 the root. In the linked list implementation I have above, it's called self.head. But essentially the same thing. What you need is just to know the first node in your list. You have to maintain that reference and you don't want to overwrite it, so keep that in mind. And what you'll usually see to loop through these lists is a copy of your self.head or your root node reference, and then while it still has a reference here, while this is not none, what you're doing is you're looping through the values, accessing them, and then you're updating what current node is as the next node. And so through each iteration, it's being the next node, the value, next node, the value, until it reaches none. And so I'll hit run here for you just so you see my 1, 2, 3 actually prints out 1, 2, 3 just like that. Now, looking at the actual implementation of a linked list, it's utilizing the class node, but it's keeping the creation of the nodes implicit. And by using append, it is checking to see if this linked list, when created, it starts with none, by the way. So when you create this linked list, it doesn't have any nodes, any information. It's just a blank slate. And all it has as its value or its pointer or attribute here is none to start off. But what you're going to do when you make your first append, it's going to create a node with that value that you put in, see that there is no head, and then make that first node you append, it's going to make that the head of this linked list. And then every node thereafter, what's going to happen is the same looping construct I discussed below. It's going to make a copy of your head attribute, and then while there is still another node linked to the current, it's going to overwrite until it finds none, and then when it the new node that it created, it's going to add that to the last node's next attribute. The only other thing of note to discuss about this implementation, well, one of two things would be to delete a node that's in the middle of your linked list. You're just going to have to be aware of how to loop through it and then maintaining your references so that you know that you can, your previous node, like there's no way for you to say in a singly linked list anyway, take the current node, if that's the only reference you have right now, and try to go backwards as the previous, right? So while you're looping, you need to maintain a reference to that previous node so that when you do delete an element, you can update the previous node.next to equal the current node.next. And that's what you're seeing here. So if there is a previous node, meaning there's more than the head, like you're not deleting just the second element in the list, which is what this would be updating, update the current next. What you're doing is you're taking that previous node.next and you're just assigning it to the current node.next. So you're assigning it the node after the current node. So that's just something to wrap your head around. It'll make more sense when you're starting to implement it yourself. And one other thing of note is when you're making this append, you may see other implementations where you can have a self.tail to maintain reference to that last node. Because note here, it actually has to traverse through all of the nodes in order to add something, which is ON, time complexity. Now, if you maintain a reference to the tail, however, and so you always have a reference to the head and you always have a reference to the tail, this changes the game a little bit in that now you can start adding things in O1 time complexity. And so why use a linked list? The main benefits are the fact that it doesn't need a continuous or contiguous block of memory. So each node can be wherever in memory, and just each node contains the reference to the next node in memory. And that kind of changes the game a bit in that it requires less. Sorry, I just noticed that there was, it wasn't green up here. That got that itch. And it's important because, say, if you have data that changes frequently and you need to add and remove nodes regularly, you don't have to worry about that overhead time that arrays take to, say, when you need to jump up to the next array size, it needs to find a larger chunk of memory, then it needs to copy all those values over to that new space and then free up the old values and clear them out. That just frees up resources for something that is dynamically changing in size. And then we just discussed how simply if you have a reference to any of those nodes, updating those references is O1 time complexity. So if you need to, say, append to this list, it can be done in O1 time complexity if you have a reference to that last node, self.tail. However, for insertions and deletions, it basically amounts to what you have a reference to. So you may have to start at the beginning of the list to traverse all the way through the list to find your element you want to insert or delete. And then flexibility is that you can definitely utilize and alter these classes and implementations of linked lists to achieve different results. And that's where we kind of lead into, stacks and queues, where basically the difference between these is you're just going to create the implementation so that it is last in, first out. And just changes how you're appending and how you're changing your references in the linked list. As well as then a queue where you have first in, first out. It basically just changes where the head is, how it's linking up the nodes, and then how it's appending or adding elements into it. So hopefully this was a bit informative. I do have more examples here, but I'm trying to keep these things short. This is Blue Collar Code, the quick and dirty, Grover. Thanks for joining.